Hello everyone and welcome to Fluid Dynamics 101. Today our topic is the topic of Bernoulli's equation. The Bernoulli's equation is very essential to fluid dynamics and plays into many parts and aspects in the fluid dynamics course. So, the Bernoulli's equation, before we even talk about the Bernoulli's equation, we must talk about an essential part that the Bernoulli's equation basically rides off of. That is the conservation of energy. So we know the conservation of energy states that energy at point 1 is equal to the energy at point 2. So let's say we have a ball here. Ball here is at point 1, this is point 2. Say the ball is kicked and it goes down the hill and it rises at point 2. After the ball is kicked, the conservation energy says the energy is conserved from point 1 all the way to point 2. So what are the energies involved? You know the energy involved is kinetic energy, potential energy. Kinetic energy is 1/2 mv squared, and potential energy is mass times gravity times height. So our conservation energy says state 1 is equal to state 2, so we know it's going to be the kinetic energy at state 1 plus potential energy at state 1 is equal to the kinetic energy at state 2 plus the potential energy at state 2. This allows us to find the velocity at any point, state 1 or state 2. You can find the height at point 1 or point 2. This is why the conservation energy is so useful when it comes to evaluating dynamics of systems. So how do we apply this to fluids? So when it comes to fluids, we know the pressure and density of the fluid is involved. So this is where the Bernoulli equation comes in. It's just a replica of the conservation of energy, just with pressure and the fluid density involved. So if we look at the conservation energy and sort of adjust it more to fluids, we're going to have this. The pressure, state 1, plus this right here, right? The kinetic energy is going to go 1/2. Instead of mass of the fluid, it's going to be density. Velocity 1 squared. Instead of mass, this goes to density, gravity, and I'm going to use z because that is what the Bernoulli equation used, but it's basically height. So state 1, the pressure of state 1 plus the velocity of state 1, the kinetic energy of state 1 plus the potential energy of state 1 is equal to the pressure of state 2 plus the kinetic energy of state 2 plus the potential energy at state 2. This is our Bernoulli's equation. States that all it is a conservation of energy with the pressure added and our mass converted to density. And this is what we apply to fluids when we're studying the dynamics of fluid systems. So let's talk about the application. Just like the conservation of energy, you can find the velocity or the potential energy at any point, state 1 or state 2. So let's say we have a milk carton, right? And I poke 3 holes in the milk carton. The milk has a density, specific density, or specific gamma. So let's say I put tape over the holes. If I were to rip it off, what do you think the flow would be if we're looking at this from the side view? Would it be like this? Or would it be like this? Well, when it comes to the Bernoulli's equation, the stream is going to come out like this. This is all based on the Bernoulli's equation because there is more potential energy above this point than this point. So the potential energy at this point is converted to kinetic energy at state 2 more than the potential energy at this point, which is less. There's less potential energy above this point, which converts less energy into kinetic energy, allowing the stream to shoot downwards. And we will see an application of this in a few seconds.